So, welcome to the afternoon session. It's a very great pleasure to have Albert Cohen giving actually two blocks on a very topical issue. Has to do with uncertainty quantification, data estimation in a very prominent context. It zooms in into one of the topics Ron was mentioning in his introductory talk. It's an intrinsically high-dimensional problems he is going to present. I don't know anybody who has a better, a deeper understanding of such problems than Albert. And therefore, I look forward to it.
Okay, thank you for a very kind introduction. So we have 4 hours, and so it is my intention to make this as a tutorial as possible, and also go into the details of the techniques of proofs of certain results. I think they are interesting in their own and could serve in different contexts. So what do we have on our table? So I will start by motivating least square method. Actually, there's not much need for motivating least square method. They're used all over. But at least explain you why I was interested in this method, what are the applications that I had in mind, why they came out naturally. And one of them is the numerical treatment of high-dimensional parametrized PDEs that could be deterministic or stochastic. And this is a chapter of its own. How do we approximate these families of PDEs? And I will focus on something which is at the same time very simple because it's polynomial. Polynomials is maybe a tool that you learn since you are very young, since you do Taylor developments. But it gets complicated when you are in the very high dimensional setting, and there's all kind of interesting techniques here. So this will take quite a bit of my time, and this will be the most abstract part, perhaps, proving certain approximation results. So we will take off a little then. That will be after the break, probably of today. And tomorrow, and maybe in the end of today's lecture, but probably mostly tomorrow, I will really go to the numerical strategies that I have in mind to build such approximation, which are based on least square. But here the main question will be really how do we sample? Where do we evaluate the object that we try to reconstruct with least squares? And I will show you how a certain notion of randomness can be useful, and this will have to do with what's called a Christoffel function. I don't think this is working. Okay, never mind. And it will drive us to a sort of optimal way of sampling, which I think could be useful in many contexts. Okay. So, 2 problems that have been of interest to me, and one is they are just examples, but one of them is an example of a generic problem, inverse problem, which is to estimate a state, a physical system that could be governed by some PDE, but all you have is data. Okay, and in that case, the system is the acoustic field generated by a source. In that case, this is a musical instrument, as you see, and you have microphone on this little array at this position y1, ym, and you record the pressure field. Okay, this is what a microphone does. Actually, in this application with acoustician engineer, what the ultimate goal was from this measurement to recover the vibrating mode of the musical instrument. But the first thing to do was to recover the acoustic pressure field in the air. And what was being done here, the first thing that was performed was Fourier analysis in time of these little signals. And then, so this is still, this is yi, this is again yi, this is the typo, yi is the position, but just you switch to the frequency variable. And you try to find the peaks, the frequency of interest, and then you focus there. So you fix this frequency. And so what you want to do then is to reconstruct, once the frequency is fixed, you have a function that only depends on the position in space, and you would like to reconstruct it from these observed data at these sites, which are the sites where the microphones are placed. So this is not a high-dimensional problem. This is a low-dimensional problem. Everything takes place on R2 or on R3. The high-dimensional problem I will mostly focus on is now more forward, related to forward simulation. We are interested in approximating in a fast, efficient way the solution to what I call high-dimensional parametric PD, by which I mean you have a partial differential equation in very general form. U is the solution, and it depends on a parameter vector, an input vector, y, by which I mean every time I change y, I have a different PD. Okay, I will give an example. And so you have a different solution. Okay? And this parameter is typically going to be high dimensional in that case. So let me give just an example, which I will elaborate later. Think of a steady state diffusion equation set on a physical domain, let's say with homogeneous Dirichlet condition. And now we're thinking of we're not interested only in how U will depend on the solution will depend on the point in space, but on how it will depend on the diffusion coefficient. In that case, for example, in this example, I take a very simple example where I assume that my diffusion function is piecewise constant on certain subdomains. So you have D subdomains of the domain D, okay? So we have a material which is composite, made of several pieces. And what we would like to understand is if we vary the conductivity, if we vary the material, how will the solution vary, okay? So now the solution depends on much more than just a two-dimensional vector, which is a point in space. It depends on all these values, okay? Right. So, and here what are we interested in doing in this problem? So the general situation with parametric PD is the following. I'm always assuming that whenever my parameter range in the domain of interest, the PD is well posed. So it means there is a unique solution. So I can define what we sometimes call the solution map, or parameter to solution map. It takes its value in the domain, multivariate domain where the parameter lives. And so the value are in the solution space. Think of the diffusion equation, then the usual space would be the Sobolev space H10, but it could be something else, okay? And these parameters, you see, they could be of very different nature. They could be deterministic. You decide what they are, you control them. For example, in that case, you could try to tune this material so that the solution has some interesting properties. Or they could be random. Maybe you don't have a good idea what these values are, but you have an idea of their probability distribution. Okay, and this is a typical situation you encounter when you want to look at uncertainty quantification, risk assessment, also inverse problem, because you may try to use probabilistic modeling to try to decide what are the plausible parameters when you try to estimate them. This is what you do when you apply Bayesian method. Okay? So in this second setting, the solution itself is going to be a random function, right? Because the parameters are random. Okay. And so my object of interest is this solution map. This is what I would like to capture numerically for all the purpose of all such application. And it's difficult. We saw yesterday in the talk of Ron that there's going to be a problem because it's a high dimensional function. It doesn't depend on one or two variables, but maybe of 100. And all the conventional methods are in principle doomed to fail, except if you identify certain interesting properties of the solution map, such as anisotropy. I will come back to that. So here our objective, as you saw, our objective is going to, in the case of non-intrusive method, which are very much used in practice, what is the idea? The idea is to reconstruct this whole solution map only from snapshots. You want to solve the PDE only for particular instances of parameters. So you have y1, ym. And why do you like to do that? Because very often you are given a numerical solver that can perform this operation. You want to do it a certain number of times, and from there, once you have these snapshots, you want to be able to process them and get a good idea of what this map is, so have a very fast access to any solution. Okay, this is sometimes called reduced modeling also. So one remark. So we call this non-intrusive because you're not going to touch this numerical solver. You're going to use it and sort of post-process the result. So that means that typically you have to think that this u of y is not maybe what you can exactly compute, but the numerical solver will, for example, give you a fine grid, finite element solution, and you cannot afford to compute it all the time. You want to do it for a few snapshots and then work from there. So you could be interested in something, in other objectives, not reconstruct, for example, the full map, but only some quantity of interest. So think of Q, for example, to be a linear functional. That means that the output is no more a function in the Hilbert space V, sorry, but it could be just a scalar. For example, it could be the flux of the solution along some interface. Or if you think of y to be stochastic, you could be interested in an average. You're not interested in all solution, but just an average, which means you're interested in an integral of this map, okay? Or an average of the quantity of interest. And all this I want to do based on snapshots. Okay, so if you think of these two problems that I gave as motivation, they are very common general feature. You have an unknown function. You want to reconstruct it from scattered measurements. These points may live in high dimension. This function would be either scalar, but it could be Hilbert space valued. Here, before going back to Hilbert space value, for a short while I will only consider scalar valued function for the sake of notational simplicity. And in both applications, measurements are costly. You cannot afford to make too many. You cannot afford to put 1 zillion microphone. You cannot afford to run your code a million times. You don't want to do that too many times. This measurement could be noisy, but actually there's going to be a lot of interesting things to say in the noiseless case. and you want to reconstruct from there. So for those who works, for example, in learning theory, I want to make an analogy and also draw the difference between the setting that we have in statistical learning. In statistical learning, let's say in the regression framework, what you are given is data, input, output, that comes to you according to some unknown distribution. And from there, you want to build a function. You want to recover a function which is a good explanation that generalizes well in a way, that will say for a general y, this is going to be a good approximation to u of y. Okay? But these samples are typically IID from an unknown density. That means you don't decide actually what are these yi. Here, in the situation I have in mind, we are the one who choose the yi. We are the one who decide where we sample, and that makes a big difference. This is what I sometimes call active learning. They will be chosen by us. So deterministically, if we have a good idea of exactly where to put them, but as I will show mainly tomorrow, it will be interesting to draw them randomly, but to draw them randomly according to a well-chosen probability distribution. Okay? So that's the difference. You have a certain responsibility in where you query. So how should you sample? How should we reconstruct? These are very general questions. Okay. And the motivation for using least square will really be based on the analysis that I will present next in the rest of the lecture about approximability. So as we will see, there's going to be you see this inverse problem, this recovery problem. There is no chance to do anything if you don't have any prior information on what this solution map can be. So you need some prior properties. Prior can be given in very different ways. They could be priors on the smoothness of the map, and slightly related, actually quite related, would be a prior on how well this map can be approximated by simple spaces, low-dimensional spaces. So this is a bit vague for the moment, but we will see very precise statement about it. I will show you that there are if we choose very cleverly certain n-dimensional spaces, then it will be possible to approximate with a very good accuracy, even if we are in high dimension. This is the good news about it. This map by an element from this space. Okay? And epsilon of n here will be a known bound that I will give estimates. And the key will be the choice of this space. And here, for the moment, and most of the lecture, this norm will be an L2 norm, okay, where rho is a probability, the measure is always going to be a probability measure, so the integral over y is 1, okay? So as I will show you, in the case of parametric PDEs, this will be the objective of a big part of my lecture. One relevant choice will be to take polynomial spaces, but here we have multivariate polynomial spaces. What are multivariate polynomial spaces? It means space spanned by these monomials, and you have to pick this monomial, a certain number of them. So if we want that this has dimension n, it means we have to pick n multi-indices nu. Okay, y to the mu always mean y1 to the nu 1, y2 to the nu 2. Okay, and as we shall see, if we pick them in a clever way, typically by looking at polynomial series such as Legendre series, multivariate Legendre series, or multivariate Taylor series, and take a good choice of term. Then there's going to be something interesting. We will recover rates that are sort of immune to the dimension. That is a significant result. Here I'm giving one instance of this result, but I don't want to elaborate on that because I will explain it later. But this is a result that says that under certain condition that I have to talk about this later because I can see that all the definitions are not given, but under certain condition I can get these kinds of rates. Okay, and the choice of these monomials is critical. So the choice of the space Vn is critical. Okay. So we have this space Vn. You can think of them as polynomial space, but they could be essentially anything. And what you want now is to use these snapshots to reconstruct something in this space, hopefully with certain optimality property, right? So remember, En of u is the error of best approximation of u from Vn. It's a projection error. And what you could ask from a numerical method that's quite ambitious is to ask that for any u, you do as good as this error. Okay, if you can do that, for example, up to a constant, of course, a multiplicative constant. Okay, of course, u minus un, because you pick un in Vn, this is always bigger than En, so there is no hope to get a smaller constant than 1. But it would be already quite impressive. I would be quite impressed if you can come to me and says, okay, I can do that with constant 2, whatever the function is, just based on this observation. I would say this would be quite fantastic, and actually it's easy to show that you cannot hope for that, but we will try to mitigate a little bit this statement. So this is what we call instance optimality, because for every instance we do the best we can. You could be a little bit less ambitious. You could ask that if the approximation error decays at a certain rate, then you ask that the reconstruction error has the same rate with a different constant. Okay? Clearly, instance optimality implies rate optimality, but this is not exactly equivalent. Finally, what is the price for doing all this? Of course, here you want to reconstruct something which lives in an n-dimensional space. Intuitively, you need to identify n parameter. Obviously, you will need at least n samples. You cannot hope to do something to obtain anything like that with less than m samples. So I would say our method is budget optimal if we can achieve all this with an amount of sample which is essentially proportional to n, maybe up to logarithmic factors. That would be good. The problem would be if you need to invest maybe a number of samples which is exponential or quadratic in n, then we would not be happy because, again, these samples are costly. Okay? So that's a general problem. Is there any question at this stage? Please feel free to interrupt. One last thing I'm asking in this method is an interesting property that can affect actually the performance of numerical method, which I call progressivity. Imagine now that we don't have just one space Vn, but a full hierarchy of space. We want to gain accuracy. How do we want to gain accuracy? By, for example, enriching the space, enriching the polynomial space by adding certain monomials, just like we do when we do mesh refinement. And of course, when we do that, when we increase, what would be problematic is if we had to resample every time. What we would like is to be able to recycle all the samples that we've already computed, right? This is what I call progressivity. So progressivity means that we would like that the cumulating sampling budget also remains proportional to n. We don't, you see what I mean by this? If every time if I do 1, then I resample 2, 3, at stage n I have n square sample, right? Because 1 plus 2 plus n is over order n square. I don't want that. Okay. So that's the general objective. So to explain what we're going to do with least square, let's do something very simple. So again, the ideal candidate to approximate is the L2 projection. This is what gives me the accuracy En of u. And you can describe it in 2 ways, by the way. You see that you can describe it by saying it's what minimizes the L2 error among all functions from Vn. Or if you have an orthonormal basis of Vn, you can also explicitly write it with in this basis with the coefficient given by this inner product. Okay? Again, rho is a measure. It's a probability measure. Yes?
Excuse me, about the previous slide, just to clarify,
yeah.
The constant in the rate optimized result, the constants are allowed to depend on u?
C0 and C1?
Yeah. Like C1.
Yeah, the C, oh, that's a good point. Very good. Yeah, C0 will depend on u, but you would like essentially, that's a good point. You would like that C1 is proportional to C0 with a proportionality which is independent of u, essentially, okay? That would be, so that would be better said this way. Yeah. One way could be to say that you multiply En of u by n to the s, and you look at the max over n, and you want that the max over n of this is bounded by a constant times the max over n of this once you multiply by n to the s. Do you see what I mean? Yeah, it would be better this way, but maybe less easy to read it.
Yeah.
Okay, so we have these 2 formulas. Obviously, we cannot compute it. The exact computation is out of reach. And the first idea you have when you have only data, pointwise data, is to say we're going to replace this integral, either this one or this one, by some discrete sum, by some quadrature. So what is a quadrature? It's just that you evaluate v at this point yi, and you put a weight that you have to think what this weight should be. Okay? So this weight is typically going to be described by a weight function that I will evaluate at yi. And so when you do that, of course, you see here you have the same object described by 2 formula, but when you discretize, you get 2 different formulas that do not represent the same thing. Okay? The first gives you what we call the least square method, actually the weighted least square method. So you minimize this least square fit. The second is what's called the pseudo-spectral method. You compute the coefficient. They are no more the same thing, right? And maybe some among you already could tell me what is the best to do actually in practice. Is this a better idea, or is this a better idea? What will perform better numerically? Maybe some have some experience on that. I don't know. We will see. I will mostly concentrate on least square, but in the end I will return to pseudo-spectral, and we'll see that there are interesting things to do. That will be mostly tomorrow. And so the main question I want to address in this lecture is really what are the spaces that we should use. I already gave a little hint, especially in this high dimensional problem. What are the good spaces? And then in order to perform well, how should we sample to reach this goal, instance or rate optimality, budget optimality? That will obviously depend on how we sample. Okay, how we choose this yi. So for the rest of this lecture, it will mostly be the first question, and the answer about the sampling and this rate optimality will come tomorrow. Okay. So now I enter this chapter of polynomial approximation, and you will see it's not always so simple, but I hope it gives, I managed to give a bit of intuition. So these are a few, this is a topic that really started after 2010. In fact, Chris Schwab came to discuss with Ron, asking a question on how to connect this with nonlinear approximation, and I joined this group, and I mean these are the first, I would say, reference where for this problem you prove results that are immune to what we call the curse of dimensionality. And maybe the reference, if you want a general reference, we have this paper in Acta Numerica from 2015, and some later things with more results. Okay. So again, I will start with a guiding example, but later on I will tell you how you can divorce from this example and what exactly you can cover. But I think it's always good to have a guiding example. The guiding example is just a steady state diffusion equation, again set on some domain D. Think of M to be 2 or 3. You are in R2 or R3. Okay. F is given to you in L2, and A is the function in L infinity. Okay. Of course, you know, or I will recall it, that first. So I think of A could be, by the way, matrix valued, but here let's think of A to be scalar valued. And so the usual assumption to have uniqueness and to apply Lax-Milgram lemma is to assume that A is bounded by below, by a number A min, strictly positive. In that case, standard theory says that there is a unique solution in this space, the space of functions with which are in L2 and which have distributional gradient in L2. Okay, this space is equipped with a norm, which is just the L2 norm of the gradient, and we also have what's called an a priori estimate that tells you that this norm for the solution is bounded by the norm of F in the dual space divided by A min. So just a one-line proof to recall. What do you do to prove something like that? You multiply the equation by the solution itself, and you integrate by part. So you get this by the green formula, and you use this condition, this ellipticity condition, to get on the left side A min times the norm of U square, and on the right side you use duality and you divide, and then you get the a priori estimate. Okay, it's very simple, very elegant, and this integration by part is actually the starting point to the theory that gives you existence and uniqueness of what we call weak solutions. Okay, so you really write this in general form by saying you take any v in V and any test function, and you ask that integral of A grad U grad V is the integral of Fv, but you could actually, when you see that, you can give a meaning to this even if F is not L2 but just in the dual of H1, 0. Okay, that's a very classical equation. I think everybody has seen that at least once. And now we start to parameterize. Okay, so remember I gave an example where this A was piecewise constant. Now I want to be a little bit more general. So I'm assuming that this diffusion coefficient have the form of an affine expansion. So we here y is again my vector and of parameters, And so we have a sort of nominal value function a bar in L infinity, and we are going to assume a parameterized form where these yj are coefficient in a certain basis psi j. So in the case of this piecewise constant diffusion, what were these psi j? Typically these psi j were the characteristic functions of these subdomains. It's obvious that that should be the natural representation, but this psi j now could be something completely different. For example, in the case of a random field, they could be a Karunen-Love basis. We could try to decorrelate this field and have this yj uncorrelated. So you can think of very different things. You can think of Fourier. Okay, so you have many. All options are on our desk. Okay, so every time I say a of y, you have to think that a of y is a function for each given y. So you should actually write a of yx, where x is in the domain, and then that would be your formula. Okay, so you have the spatial variable, which is x, y is a parametric variable. And so similarly, the solution u of y, when I write u of y, it's itself a function of x, right? But most of the time I will omit the reference to the spatial variable. So when I write u of y, it means it means the whole function. Okay? And you see that if I make a little change of variable, I'm always going to have that this yj range in finite intervals. Otherwise, I could destroy ellipticity. So up to changing these psi j, up to renormalizing them, I can always assume that this yj will range between -1 and 1. So there's no loss in generality in thinking of them living in this box. Okay, it's a very high dimensional box. Tensor product domain, but very high dimension. Okay, and what I'm going to assume is that whenever I pick a parameter in this box, I have ellipticity. So I'm assuming that a of xy, this object, is always bounded by above and below, independently of x in D and y in y. Okay? This means that every time I pick y in this box, I have a solution which is uniformly bounded by the Lax-Milgram estimate. Okay? So now we have a sort of idea of our solution map, and we would like to approximate it. Okay? Now we're going to do it with the simplest thing we can think about, namely polynomials. Okay? So, as I said, the idea is going to be so what is a polynomial? For me, it's just a sum of monomials. And y nu again means the product of yj to the new j. But let's be careful here in the case where you have infinitely many variables. In order that these things make sense, that this product converges, it's not trivial. I will always assume that this nu is finitely supported. Okay? So it means the total degree is finite. Okay? So it means only finitely many nu j should be non-zero, sorry. Only finitely many nu j should be non-zero. All the others, nu j, are 0. But it could go to arbitrarily large j. All right, this is what I call a polynomial, and nu n is lambda n is some set of finitely supported sequences. Okay. One thing that you should bear in mind is that because u of y is a function for every y in a Hilbert space, because the solution map takes its value in the Hilbert space, this polynomial takes its value in the Hilbert space V. So that means that these coefficients are not numbers, they are functions. Okay? Looks a bit weird, but it's not so. It's quite natural if you think about it. Okay? So UN is actually something that you could describe as living in the space, which is this tensor product. These are polynomials, but V-valued polynomials. Okay? So V is the space where the coefficients live. Right, so this is what I call a polynomial, a V-valued polynomials. And now I want to build a good one that approximates well the solution map. And the strategy will be to expand this map into an infinite series. And there's many options: Taylor, Legendre, Chebyshev, Hermite, in the case of Gaussian probability distributions. I will talk about it in the end. And then to take this series and to truncate it by picking this term in a clever way. So the choice of this truncation set will be very critical. Okay? So the picture you can have in mind is what? Let's see. Yeah. You're going to have expansions, and each term of this expansion, if you think of Taylor expansion, it will be indexed by a certain multi-index mu. But mu is has all kind of variable, u1, u2, etc. So you have to think that you have a lattice, an integer lattice, in infinite dimension, or in very large dimension. So here I only draw it in 2 dimensions, but you have to imagine this lattice to live in many, many dimensions. And the question, the critical choice will be how to truncate, where to select, which index do I want to pick. Okay? What is the way to choose this boundary, if you wish. Okay? That will be our questions. Before I go further, let me say something about the measure of performance. So there are several ways to measure performance. We can be interested in doing a good job uniformly over the parameter space, so work in L infinity of y with value in V, so it means that we want to control uniformly on y the error in the Hilbert space V. Or we could work in the mean square sense, especially if we have some probability measure which is naturally associated to this parameter, we would look at this L2 norm. Okay? Which means if y is really a random parameter distributed according to rho, this means that we're looking at the expectation of this quantity. Okay? And, right, let me notice that because it's a probability measure, the L infinity norm is always an overkill. Okay, a worst case estimate is always something that controls the mean square estimate, right? Because it's an average. It's always less than this. So it's always more pessimistic. So I'm going to first show how we obtain certain worst case estimate, and I will say also how we obtain sharper mean square estimate. Okay. So as I said, the critical question is how to pick this set lambda. And that is going to drive us to notions in sparse analysis, sparsity, which are very general and that we will apply here. So sparsity now. How am I doing time? Oh, good. So what we are doing, if you think about it, is a very general idea in a way that could apply in different contexts. We have a big representation. We can think of this as an infinite vector, a sequence of terms, and we want to pick inside the right ones. Okay? So think of a very simpler scenario where all these guys here would not be functions, but just numbers. So think that you have a big vector, let's say in LQ, in some Lebesgue space LQ, where F could be any countable index set. And what are you trying to do? You are trying to approximate this sequence by a sequence which is supported by a smaller set, a set of size n, an n-sparse vector. Okay. This is a very general question. And if approximation takes place in LQ, the solution is, of course, clear. We are going to leave, to put to zero every coefficient except the n largest one. That's obviously what we should do. Okay? But now how does this perform? Can we say something about how effective this is? And the answer is yes, and it's due to generalization of an observation initially due to Stechkin. But Volodia complains about Ludia Temniakov that we call this the Stechkin lemma. He says this has nothing to do with, it's not due to Stechkin. I would say Stechkin for a particular case of that. Okay, so what is this lemma telling you? It's a very simple lemma. It says, assume that you have a little bit more summability. Assume that your D is not only in LQ, but it's in LP for some P less than Q. This is stronger, of course. For example, it's more difficult to be in little L1 than in little L2 or little L infinity. Then the error that you retrieve from this process will decay at a certain rate, n to the minus s, actually n plus 1, where s is the discrepancy between 1 over p and 1 over q. And actually the constant c is just the LP norm. So this is a very nice result. It tells you that if you decide to use this particular process of approximation, its convergence is governed by a bit of extra summability. And okay, it's an implication, but it's almost an equivalence. Bear with me. If you had to, you could prove an equivalence if you change the space into something called a weak LP space, which I don't want to discuss, but it's not so different. So I'm just giving a two-line proof to convince you of this fact. If you want to prove that, what do you do actually? What are you doing when you take the n largest term? Why is this true? When you take the n largest term, what you are actually doing is you are rearranging this guy by decreasing order. You are permutating them so that they are in decreasing order, and you only keep the n first. Okay, so call d star k this decreasing rearrangement. And now you can compute, because d minus dn, what it is simply the tail of this thing after you remove the n first. The n first are the n largest. That's the same. Okay. And so now I'm going to do something here. I'm going to artificially introduce this power p, okay, and use the fact that this is the decreasing rearrangement. So this d star k for k bigger than n is always less than d star n plus 1, and because you have a positive power, you can put it out. Okay, so you have d star n plus 1 to the power minus p. This is because I took the decreasing rearrangement. And what you are left with is the sum of this guy, but the sum of this guy, because it's a rearrangement, is bounded by this. So you are left with estimating this guy. And this guy, again, you can estimate simply by remarking that if you take n plus 1 times the n plus 1 star p, because again you took a rearrangement, this is less than the total sum, Cp. And now all you have to do is to combine these two things. So you combine these two lines, and you see that you exactly get what I wrote here. Okay? So it's not difficult, and it shows you the role of summability. One remark is that if you would like to go to very large value of S, if you would like to ask what is the condition that will govern, for example, decrease like n to the minus 2 or n to the minus 3, very quickly you see that this will drive you to value of p which are less than 1. So it's a bit unusual. You land into conditions which are not convex, not described by convex spaces, but it's perfectly licit to consider this condition. I mean, this is so we're going to be interested in these conditions, this summability condition. So the message of this slide is that sparse approximation is governed by summability, and summability is described by how small this p is. Okay, the smaller the p, the larger one of the p, and so the larger the rate of decay. Okay, that's for sequences of scalars. Now, if you remember, our problem is a little bit more difficult. We have a Taylor expansion. We are going to look at polynomial expansion. So things of that sort. So think of this thing as something like this y to the power nu, and these are the coefficients. Okay? And now we would like to understand what happens when we truncate. Okay? But we can actually use Tetskin lemma. So think, for example, let's look at the L infinity norm. And think, for example, that the case where these functions are all bounded by 1. This is the case in the case of the y to the nu, because y to the nu is a product of yj to the nu j. All the yj are between minus 1 and 1, so you have this. Okay? So now you want to look at this thing. If u is a complete series, you can just choose triangle inequality, and now you use that this function as a function of y is bounded by 1. So you are left with the L1 tail. Okay? So with the tail of the L1 tail of these norms. Okay? If you work in L2, if you are interested in the estimate, in the mean square estimate, and if this phi nu happens to be an orthonormal basis, so think, for example, of Legendre polynomial, then you can do something a little bit smarter than triangle inequality. You can apply Parseval equality. So you get something like that. And because it's a tail, you just get what's not in lambda n. So now you see that we are exactly in the situation that I described in the previous slide, because in the previous slide I had to look at the sum, the tail in LQ in general, and here Q is either 1 or 2, and these coefficient d nu have been replaced by these norms u nu. Okay? So you see now, for concrete choice, our relevant question will be what are the smoothness property of the solution map that will tell you that these coefficients have a certain summability, because we know that summability is going to imply some rate of decay for this. Okay? So there is a long chapter on that in low-dimensional approximation. In low-dimensional approximation, for example, when we approximate images or one-dimensional signals, if you expand in nice bases like wavelet bases, then we know that the summability of the coefficients is characterized by membership in certain classical smoothness space. We know that if your function lives in a Besov space of a certain type, so Besov space are generalization of Sobolev space, then you will have such summability property for wavelet coefficient. Now we are in a completely different setting of high dimensional function. we're using tensor product polynomial basis. What is the vehicle? What are the properties that will guarantee sparsity? And as I will show, this will be governed by the anisotropy of this function. Okay? So you see we have three, there is a, you see the logical chain. Okay, I actually went backward in this chain. I say, okay, we want to have some sparse approximation. We want to approximate by a polynomial. We are going to use the best n term. Then I ask, what are the conditions to have this performing well? You need some ability of the coefficient. And now I'm asking, what is the condition to have some ability property for this coefficient? And I'm saying this is going to be governed by anisotropy features. This is what I want to go to next. So I want to return to my main guiding example. How am I doing? Maybe this is time to take a break, because, yeah, I think it's a good time to take a break. A 5-10 minute break. Okay? And I will give then the main theorems that will be my next hours. All right?